Wow. Hi, everybody. Welcome to our April 2023 Cannabis Industry Meetup. I'm Jen Burns. I'm head of the Business Insight Center at the Central Library. And on behalf of the library and your Hemp Lab, I welcome you to our program tonight with the very exciting Dr. Jason Matlock from Fluence Lighting. And he's going to go over everything that you ever wanted to know about horticultural lighting. So without further ado, Jason, take it away.
Hey, everybody. So yeah, that was kind of how I started building this presentation. The prompt was, what do you need to know about horticultural lighting? And as I built it, I realized that that's a massive amount of information. So to make this digestible and to provide some focus for the presentation, we've actually broken this down into two parts. So tonight is part one, where we're really going to be looking at how do you measure, describe, talk about light? What's the equipment that you use to produce it? How do you make a lighting design? How do you interpret a lighting design? And there's a little bit of a case study here to kind of show what a small amount of supplemental light can do. So yeah, really the focus of this is, by the end of this talk, are you in a position to be able to understand what somebody is presenting to you if you are asking them about lighting and they produce a quote for you? So it's a fluency, no pun intended, in the nuts and bolts of horticultural lighting equipment. And then the intention is to have a second part here sometime in the near future, where we go a little bit more into how light interacts with plants, how you can use light to steer and drive production, and what some of the practical considerations are in your cultural environmental management practices towards getting the best results from that lighting. So to start off, who am I? Why should you listen to anything I have to say? As she mentioned, my name is Jason Matlock. I have kind of a diverse career that's bounced me around a lot of cool places and landed me in this specific role. So I did my bachelor's degree in chemistry, master's and PhD in agricultural science at Michigan State. I started my professional career off actually working as a quality control chemist for a winery. Found my way into the world of beer manufacturing. I ran a small brew pub called the Round Barn Brewery in Michigan. Was the youngest head brewer in the state. And then I ended up working at Founders Brewing Company during a very large scale up. If you're not familiar with Founders, they're one of the larger craft breweries in the United States, definitely the second largest in Michigan. So from beer, I got exposed to a lot of production-based environment practices, learned a lot about optimization, how to maintain schedules. Through the winery, I worked in vineyards, managing hundreds of acres of our own grapes, coordinating thousands of acres of production vineyard from contract laborers. So I get a lot of overlap between cannabis and these industries. Got involved in cannabis through Michigan as a caregiver, scaled up through that program, got involved in commercial production, helped start Redbud Roots in Southwest Michigan. Worked in construction for a company called GICS, Green Industries Construction Services, which designed and built turnkey cannabis facilities. So I did some work on the actual facility design and construction side. Was the director of operations for Camp Cannabis in Missouri. And now I work for Fluence Bioengineering as a horticulture service specialist. So our role is to act as horticultural consultants for our customers, to work with them to solve operational challenges and to ensure that they are successful when utilizing our products. And part of that work involves doing outreach and education. I also sit on the cultivation committee for the Cannabis Association of New York, which is how I got plugged into this program. So that's kind of me in a nutshell. Let's dive into it. Let's start off. We need to know how to talk about light. There's a lot of words out there to describe light. What's important to us is to recognize that we're talking about a specific application. We're talking about light being used to grow plants. So the first thing that we need to consider is that we're talking about PAR light, photosynthetically active radiation. That's the portion of the light spectrum that plants use to do work, produce food, drive their metabolism, and make decisions about what the environment they're in is like and how to respond to it. So that's somewhere between 400 and 700 nanometers, which is really red to blue. It corresponds roughly to what you and I see as the visible spectrum. Some nuances to that, but that's the gist. So when we describe intensity, when we describe how much light or what light we're using, we're always referring to that bandwidth of light because it's the useful portion. Other measures of light outside of horticultural lighting don't do that. So the next thing that we need to think about is how much light is a fixture producing. So that is your PPF, or photosynthetic photon flux. Flux just means amount of stuff getting spit out per unit time. The output of a fixture, sometimes useful, sometimes informative, but really what we care about is what is happening at the plant level. So perhaps the most useful metric for measuring light is PPFD, which is photosynthetic photon flux density. And that's how much light is hitting a known area over a known period of time. In this case, that's standardized as the number of photons that are hitting a 1 meter square area. And that's a lot more relevant because it's standard from fixture to fixture, and it's something that relates to what's happening at the crop level. The next thing that we want to think about is DLI, which is daily light integral. So where PPFD is a measure of instantaneous intensity, right? How much is coming out right now? DLI is more about how much has come out total over the course of a day in that area. So when I think about this, I like to use a rainstorm as an analogy. So if we think of the light fixture itself as a rain cloud, that's where the rain's coming from. That rain cloud is spitting out a certain amount of photon droplets, light droplets at a given time. And how much it's spitting out is kind of like how hard it's raining, right? If it's drizzling or is it pouring cats and dogs? That's your PPFD. How hard is it raining? Then how much water fell into a bucket while it was raining? That's my DLI. So you can see that you can have fluctuations in the amount of light that's coming out over the course of time, just like you can the amount of rain that falls, and achieve the same amount of material in your bucket. So the last thing that we want to consider when we talk about fixtures themselves is efficacy, right? We're using electricity to produce light, and there's certain levels of efficiency in that conversion. Very inefficient fixtures are going to produce less light than more efficient fixtures for the same amount of power. So it's important to consider efficacy because you pay for that electricity. When we think about these measures, what we've seen in the research and in practice is that PPFD is important for affecting plant growth, and there are ranges that plants tolerate well, but ultimately the growth pattern of a plant is really driven by DLI, the total amount of light that a plant receives on a given day. So that's sort of our vocabulary to start with. Let's start adding some ranges of these things so we can calibrate to some numbers that mean something. So starting with PPFD, the how hard is it raining part. PPFD is broken into three pieces, right? It's the number of photons, so a quantity, how much light per meter squared in an area per second, unit of time. And that ranges on the range of 0.01 micromole per meter squared per second, which a lot of times we just abbreviate as PPFD. So from 0.01 PPFD up to around 2200. So 0.01 is like moonlight. Then you kind of move up to the ones, the single digits being candlelight. You're inside your house is usually around 5. If it's a cloudy day outside and you have some lights on. Under a tree is around 100. A bright, sunny summer day, somewhere between 5 and 1500. And some of the brightest places on Earth are going to be just over 2000. So to give you an idea of the practical range, that's what we're dealing with. So now, when we talk about DLI, there's a couple of things to break down in here. So first off, DLI, right, same unit structure, except this time instead of micromoles, it's moles. It's just a bigger unit, like grams to kilograms. So it's stuff per area per day instead of seconds, right? So when we look at that range, probably the easiest way to describe that is to ask how much does cannabis need at each of its life stages. In clone, we're looking at a DLI of around 3 to 5, which is equivalent to about 50 to 80 micromoles intensity delivered over a 12 to 18 hour period. For vegetative, it's like 26 to 38 moles, which is a light intensity of around 4 to 600 on average over an 18-hour period. And then in the flowering phase, that's where we're dealing with a lot more light. That's like 38 to 65, which is equivalent to 9 to 1500 micromoles. Just to give you guys an idea, tomatoes, which we think of as a pretty light intense greenhouse crop, about 25, maybe 30 DLI for growing a healthy tomato in a greenhouse. So big appetite here. When we think about DLI, the thing to remember is that DLI is very seasonal. We'll get into this a little bit more in detail, right? But since we're talking about greenhouses in New York, that's something to think about, is the amount of light that you get naturally over the course of a day is going to change with the seasons. On the outdoor side of things, it's usually 30 to 35 during the top portion of the summer, and it can get down as low as 5 or 6 in the winter. So just like I was saying with the rain as well, you can have different amounts of intensity throughout the day and achieve the same DLI. Oh, well, here we go. I meant to tell you guys this anyways. I thought I took the slide out, but here's a little bit of a calibration for you. Microgreens 5, high wire crops 25. So again, cannabis sits way past this. All right, let's continue on with talking about DLI. So this is a course largely driven for New York. So here's some data taken from Syracuse. So first off, upper left corner. I'm going to walk you through this stuff. Upper left corner, these red dots at the very top. This is the DLI for every day averaged over the last 5 years in this area that you see outside. So you can see that when we're January, February, December, in that range, that winter months, we're probably somewhere between 3 and 8 DLI. That means we got a lot of light to make cannabis happy. And in fact, if we look at this, only really during June, July, and August are we over 30, which is what would be considered necessary to consistently produce economically relevant yields of flower market ready product. The rest of the year, we're short. So gotta either make up that difference with supplemental lighting or build a business model that is either seasonal or that accounts for the fact that you're going to see decreases in quality and yield, and you're going to have a more variable crop. This also affects how the plant grows. So that's outdoors. But what matters is what's happening inside of your greenhouse. So if we come down here, we're going to talk a little bit about transmissivity. So you've got glass that light has to get through. That glass allows only so much light through. A lot of times new glass is somewhere in 90, 95% range. Old glass is 70 or 80. And that's how greenhouse advertisers will tell you you rated their greenhouse. But there's other stuff that's in the way. So by the time you get to your crop, you may be down 50, 60, 70%. And furthermore, all things are not created equal, right? You've got a shade curtain here, you've got a fan. So the shadow on this crop here may be 30 or 40% of the natural light getting through. So all of a sudden, this red peak of natural light is knocked down further and further by the time you measure what's going on in your greenhouse. So when you design for lighting, it's important that you design site specific and you take actual measurements inside of your greenhouse so that you're accounting for your conditions. And that's something that's really important for a lighting designer to do. If we come over here and you start to say, well, how much light do I need? Just to get a tune in this graph, what we have is different target DLIs ranging from 25 to 40 at different transmission rates. And it shows you throughout the year what supplemental light level you need to achieve in order to reach that DLI. And of course, during the summer, you don't need as much as in the winter, but in general, if we were to say 35 DLI as our cutoff, you could see that we need somewhere around 500 ppfd in a high transmission greenhouse, and probably closer to maybe 600 in a low transmission greenhouse. So now that kind of helps calibrate what you need to be thinking about when you're looking for supplemental light. So once you know what you're trying to get to, now you got to figure out how you get there. And there's a lot to think about when you're doing that. The first thing is that just like measurements are site specific, so are lighting designs. It's really important that you have a project specific lighting design that takes into account your space. And we need to pick the right fixtures for the job. So when we talk about fixtures, one of the biggest things that we talk about is beam angle and mounting height. So all fixtures spread light out in a cone to some degree. Now that can get wider or narrower. And so we talk about the beam angle. 120 is a pretty standard number, but what that really matters for is that there is a certain height above your canopy that any given fixture is going to produce the optimal coverage. We don't just want to achieve a certain intensity. We want that to be spread evenly throughout the crop. If it's not, some crops get short, some crop gets tall, some crop needs more water, some crop needs less water. You introduce variability into your growing practices, and that can make life hard for a farmer. So we want to have even coverage. Just to kind of show you what that looks like, these are called isoline diagrams. So they show you the pattern of light. They're kind of like topography maps, elevation maps, contour maps, but for light. So here's an example of 4 fixtures hung very close to a surface. It's really high light, 3000. You kill just about any plant you put under these. And it's very narrow, spotlight. We zoom that back a couple of feet. Now it spreads out. We have lower intensity, but still pretty high. But you can see it's still very concentrated and it drops off very quickly. When we hit 7 feet away, now it's gotten much more even. There's still some drop off, but we're mostly between 240 and 360. So much lower intensity, much higher uniformity. And if we go way, way out, it gets really, really uniform, but the intensity is so low that it's not useful. So there's a balance point. And part of a good lighting design approach is finding that optimum so that you're getting good uniformity, but you're making the most of the light intensity that you produce. The other big take home here is that once somebody designs a light plan for you, it's really not a good idea to change it. So a little bit of a public service announcement for someone who works in lighting. They were put there for a reason. Don't tinker without asking. Always call up the manufacturer and say, hey, I want to make some changes, and have them walk through with you. Let's talk a little bit about light designs. So when you get a light design from a lighting manufacturer, you should have a couple things come with it. And if you're bidding out the job, which you should, right, to get the best value, it's important that you line all those up and make sure that they are apples to apples comparisons. There's a lot of apples to oranges out there, and not a lot of people are really helping you see that difference. So a couple of things that I want you to just look out for a good design. First, there should be proof that this design matches what your room looks like and some sort of rendering. You'll get a layout that's 2-dimensional that'll show your benching and where the lights go with dimensions for the spacing. So, just verify all that makes sense. But once you have that, then what you're going to get is you're going to get some measure of average intensity. And we usually talk about designs in terms of their average intensity. We'll say this is a 1200 ppfd design or a 500 ppfd design. So we talk about the average, but the average can come from something very uniform and narrow, or something very wide with extremes. So it's really important that we have other measures to check how uniform that design is. And we get those by looking at the max and the min along with the average and asking ourselves, how far spread apart are those? 2 quick rule of thumbs for that. If you take your average over your max, you want to see a value over about 0.8. And if you take your min over your max, you want to see a value over about 0.7, just as kind of a guideline. The next question you should be asking is, where were these numbers derived from? The average of what area? If I went and I snapped measurements just from the center 4 fixtures, well, that's going to look great. And in fact, that's what I did over here. You can see it's 1440, nice and high, almost no different, super uniform. Wow, that looks great. What a great value. Well, yeah, because it's in the center of a lighting design. What we care about is what's happening more broadly. So, when we look at the edge is the other extreme, right? Very low, huge range, not very uniform. So if we just looked at the edge, that would look terrible. And the truth is the edge is always kind of off, right? You have a wall, the fixtures stop, they're not overlapping. So you almost always have challenges with the edges. So what you really want to look at is, something roughly about 80% of the canopy. So come in from the edges a foot or so, and you want to take an average that represents that non-edge canopy across the space. And if we look at this particular design, you can see, right, it's around 1270. Uniformity is still a little low, right? Max min is 0.69, so it's close. Average over max is 0.6. That's below our target. So this design is starting to get there, but I would say, hey guys, you need to go back and do a little bit more work on this. So I just want you guys to be aware that there's a lot of different ways to present these things. Make sure that they're standard, make sure that they're done appropriately. And then ask yourself, what other assumptions have they made in these? Did they make the walls reflective, et cetera, et cetera. So get as much information as you can. All right, so let's talk a little bit about fixture formats. So there's a lot of different shapes out there. Kind of talk about the general families that we have. In the world of LED lighting, probably one of the first things we saw was this multi-bar fixture, right? Fluence calls it their spider. There's a lot of companies that produce these. They're designed for high intensity, close proximity deployment, right? This is really built for vertically tiered cannabis operations in indoor environments. I see these hung over single tier crops. I don't advise that. There are better formats for that. These have to be very close. And so particularly in a greenhouse, that means you have a lot of wire hanging down. You've got a lot of electrical equipment and material in your way, blocking natural light. So you form almost another ceiling that you have to deal with. It can interfere with curtains. So I strongly advise against using this format in a greenhouse space. Its cousin, the multi-tier low intensity setup, you'll see these up formatted for Dutch trolleys. They're usually 4 feet by 2 feet. They're designed to fit onto wire racks, trolleys. They're used in vertical farms. These you might use in propagation if you have stacked propagation spaces to achieve appropriate intensities, and they might show up on your bill of goods. Where you're really going to see your bread and butter in greenhouses is fixtures like these two down here. There's a linear top light format. We call this the Viper. There are other versions of this. They're narrow, they're long. They're designed to fit under a truss or a purlin or a rod without blocking light. You tend to need a few of these to make the light work out. So they tend to have a high concentration of fixtures, and they run somewhere in the 500 to 800 watt range. What we're seeing more and more of, and this is a relatively new release also at Fluence, are these HPS replacements. So these run at around 1,000 watts. They're designed to swap into an HPS bay as a direct replacement with minimal modification. We're also seeing these start to get sealed and washed down ready for deployment in greenhouses. So something like this is probably what you're going to see and should be considering. They're also designed to sit up away from the crop. You're going to lose a little bit of efficacy from the throw, but the beam angle is narrower, and they're out of your way, which also means that they're out of the way of sprays and other things that you're going to do. So the light is protected from any sort of damage that would cause. The last kind of light, this is sort of a specialty thing, but we're starting to see the inner canopy, sub-canopy lighting technologies from tomatoes migrate over into cannabis. There's some preliminary work being done by us and others, as well as by some influential growers. showing that this is a promising technology. So it's worth talking about, worth potentially exploring, something I'm personally really excited about. Okay, so we've talked about fixture outputs, formats, arrangements, how to talk about light intensity. Let's talk a little bit about light quality and how that affects the efficacy of a fixture. You're going to have to choose a spectrum, right? A spectrum being a mix of different colors that comes out. The sun is all colors evenly represented. So we're already deviating from that. What's important to know is that blue photons, blue light, takes more energy to produce than red photons. All light moves at the same speed, but as they do that, they wiggle. And that's where the wavelength comes from. It's how far are they traveling as they wiggle up and down. So red light wiggles less than blue light, so it carries less energy, which means that if you're gonna knock out a red photon and shoot it somewhere, that you need less energy to move one photon than you do to do the same thing with blue, which wiggles a lot more. What this means is that if you shift a spectrum more and more and more towards red, you're either going to produce more light for the same amount of power, or you're going to spend less energy to produce the same amount of light as a spectrum that has more blue and green and other colors. So when we're talking about the energy that you spend, what we're talking about is efficacy. And efficacy is measured as the amount of photons, micromoles, that you make per unit energy, joule. And you can express this as watts and other things, but usually micromole per joule is what you're talking about. To give us some calibration, the workhorse spectrum from Fluence is what we call our broad R4. This is about a 40% red with the rest made up by the other colors. Comes in at about 2.7 micromoles per joule in our commercial fixtures. Now, we produce fixtures for other cropping systems as well. And particularly in commercial agriculture, they're very concerned with how much they're paying because they make pennies per square foot. So it matters that you have an efficient spectrum, perhaps more than the impact of light. So we have 60, 80, and 90% red spectrums, and you can see they become increasingly more efficacious to the point where the R9B spectrum is about 50% more efficacious than the R4. So you might say to yourself, well, boy, I'd love to spend less money on the same amount of light. That sounds great. To an extent, there are consequences to shifting high red in cannabis that are worth being aware of. What we have seen is that as you increase red light, there's sort of a point where, particularly in higher intensity applications, you get morphological differences. You see foxtailing, right? So little dreadlocks coming out, and you see photo bleaching, which if you look down at these photos, you see these white tips. That's photo bleaching. So the red light actually physically destroys the pigments. Well, it leads to a process that destroys the pigments in this cannabis, and it bleaches these out. And when they dry and cure, they turn into this sort of brown, moldy looking material. It's not very attractive. Chemically, we don't really see a huge difference in the bud itself, but visually it's unappealing, and it seems to command a lower market price. So you have to ask yourself, does that matter to me? You can see here, just these are the same strain grown under an R4 at high intensity and then an R8 under high intensity. Then you can just see, right, they're morphologically different, and this one bleached while this one didn't. The other thing that's worth noting is that as you shift red, you create a less natural working environment. The human eye is best operated under white, broad light. As you start to go pink, it's harder to resolve colors. And so that can become a challenge when you're trying to perform detailed tasks. So things to consider as you do that. The other thing to consider is that, particularly in greenhouses, we tend to grow larger plants. It's really important that we get light penetrating deep into the canopy of cannabis. The flowers are photosynthetically active, so they need light to develop effectively. Red light, blue light gets absorbed very well at the top. Green light, yellow light is what penetrates deeper into the canopy and drives that mid-low canopy development. So as you shift further and further red, you have less light fractionally getting into that deeper canopy. So you can have more asymmetric development of your plant, under those spectra. We just talked a little bit about quality here. So, we're going to move into the question of why should you put light in at all? And the short version is because light is associated with yield and quality, which are the two primary economic drivers for cannabis businesses, right? We want good looking product and we want a large amount of it for the same amount of square footage. The more efficient you are, the more likely you are to succeed in this increasingly commodifying market. Here's some photos just showing, same cultivars grown under low intensity and high intensity light. And you can see, right, they're stretched, they're larvae. This is not going to sell well. It's not going to process well. And under a high light environment, you get a compact nog, more trichome development, higher potency testing, and you'd command more per dollar or more dollars per yield out of that. The other thing to recognize is that cannabis has a voracious appetite for light. So this is some of our research at Fluence. Others have produced similar research, so this is pretty well validated. You notice that the axis here is 1100 to 2500 ppfd, right? So that's something like 30 to 80 DLI. These are three different cultivars. And you can see that while the absolute yield of each cultivar changes, that's no surprise, the response is fairly consistent up to around 2000. So you get a near linear response in yield to increasing your amount of light, which 1% light equals 1% yield has been an adage in agriculture for a very long time. There are tons of caveats to this, of course. Optimization is critical. I'm going to talk about this more in part 2 down the road, but the reality is that there's almost always a fairly short sub-year ROI to investing in light, and that oftentimes light is the lowest cost to expanding your production. It certainly is often a lot cheaper to put more light in and upgrade the space than it is to build additional physical square footage. So as a closing exercise, I want to get into a case study. This is a greenhouse that I put in some light for a trial. It's in Florida. We ran this past October through December. We actually did 2 more runs. We're finishing up our 3rd run. Results seem pretty consistent. So this is some data from that. Give me one moment to wet my whistle. I'm going to walk you through this. There's a lot going on in this slide, so bear with me. But the first thing here is, we've got these light depth greenhouses. They were running natural light alone, and they wanted to see what would happen if they added in some supplemental light. They were power restricted, so they didn't have the ability to run the big, large quantity of light that we design for a lot of our greenhouse customers. They have limited environmental control. So we put in about 250 ppfd worth of light, pardon me, which is, it's not trivial, but it's not huge. So I would call this a modest investment in supplemental lighting. They compared us to a competitor. Not here to preach on us or others, so I blacked that out. We're going to talk about things just in terms of the supplemental lighting. But we had a fairly similar power draw. The increase in light was fairly similar, so both of us were relatively similar. The only real difference was in spectrum. So when we had the measure light throughout the day, this is just kind of showing you, right? We had a fairly consistent increase of around 200 to 250 ppfd relative to the natural light treatment, and that Fluence and the other lighting were relatively well mixed in terms of what they were developing. When we looked at the harvest metrics, what we looked at total yield. We looked at total yield, just everything that came off the plant that was flower. That's our gross yield. We looked at market flower, so that was material that they selected based off of size and appearance. So we could measure the percentage of the grade A, the market flower, compared to the total yield. We looked at that both in terms of just raw yield and yield per unit energy. And we also looked at the THC content in both the top colas and the bottom colas, and then just the whole plant in general. And what's important here to note is that yield under supplemental light was 1.4 to 1.5 times greater than under natural light. And that improvement really occurred in the market flower portion. So we produced more flower, but we produced better flower. The fraction that went to extract and pre-rolls remained fairly consistent. The increase was almost exclusively in the top to mid canopy development and creating more market-ready flower. And perhaps most interestingly is that as we added light, we increased potency. These cultivars today are being bred to produce dry weights over 30% of their biomass. And that's a lot. And you're asking a lot of the plant to do that. So oftentimes potency is restricted by light availability because they just need more energy to reach those high levels. So you usually see an increase in potency as you increase light from a low light environment. And that increase in this case was between 2 and 4% weight to weight. The other thing that's important to recognize here is that not only did we increase yield and we increase quality, but that increase in quality increases the market value of this product. So Florida is a tight market and it's heavily driven by THC. So they asked us, well, how much is it driven by THC? So I answered that question. So I'm going to walk you through this very briefly just to kind of show you this. I went out and I collected the price and THC level for every 8th package that was listed on Weed Maps in 5 major markets in Florida. And then I binned them out in $5 increments to see what percentage of each one of those categories fell into a certain price range. And I did that for 16 to 18%, 18 to 20, and 20 to 22% THC bins, because that represented what we saw under Fluence, the competitor, and Natural Light. So then I averaged that out to say, all things being equal across the market, how much is THC affecting your price point? And the answer is quite a bit. So we saw a 4 to 11% increase in retail value relative to the Natural Light levels. So you can see, right, 16 to 80% was about $40, around 42 for an 18 to 20, and it jumps up to 45 for 20 to 22. And the other thing I saw is as you kept going, right, that price point continued to elevate. So quality drives price point in a matured, commodified market. And lighting can have an impact on that. And more importantly, the thing to recognize here is that the light intensities were relatively consistent here. So the only real difference between us and the other treatment was the spectrum. So what we can see is that spectral choice does have an impact both on yield and quality response. So it's something that should be considered and discussed with your lighting providers as you're having these jobs bid out. And just to contextualize this is the wholesale revenue difference for one of these greenhouse bays. You can see that under natural lighting, getting about $500,000 for a turn of that greenhouse. When you jump up to supplemental lighting, you're seeing just under $1 million up to $1.25 million off of one of those turns. And on 5.5 turns a year or so, that really equates to a 6 to 8 month payoff. And that includes the electrical work, hanging unistruct grids, and the downtime that it takes to install those lights. So a relatively small investment in lighting can have a very quick impact, meaningful impact on your product, and it can really help you drive yourself forward in terms of quality and being competitive as a high quality brand. So with that, I got one more thing to preach here. Obviously I'm an LED lighting manufacturer, so I preach LED, and there's a reason for it. This is taken from the regs that are being put out for New York. Part 125 says that horticultural lighting must be selected from lights that meet the Design Light Consortium solid state horticultural lighting qualified products list. So there's a group out there. It's a third-party testing registration group that we all submit our fixtures to for review. They have a bunch of standards for whether it makes it onto the approved list or not. There are many organizations and governments that require you to use products that come from that list. What's important about this is that the rules say that you can use existing lighting if it's already in place at the time of your conditional licensure. So if you have HPS fixtures already or something else, you can use them. But if they are less efficacious than 1.9 micromole per joule, then you have to have a transition plan in place for the first year. And if you add any new lighting, it has to meet the DLC listing requirements. Why that's critical is that on March 31st of this year, so just last week, the DLC listed version 3.0 of their listing criteria. And one of the major changes is that to be listed on DLC, you now have to have a minimum efficacy of 2.3 micromoles per joule. Why that's relevant is because the most efficient HPS CMH technology out there is about 1.9, maybe 2 on a fresh, new, expensive bulb. So they've effectively made it so that anybody who relies on DLC listing as a standard will no longer be able to use non-LED lighting technologies at this time. But that shouldn't really be surprising. It makes a lot of business sense. It's a smart thing to invest in. The science is there, and the results are there in the market. The quality is there in the market. And then when we look at Cannabis Business Times 2022 business or cannabis industry lighting survey, what we're seeing is that across the board, propagation, veg, and flower, more than 70% of the industry that has lights installed are driving that with LED technologies. So I really encourage you strongly to look into that technology and reach out to several vendors to learn more about it and to consider your options. All right, so I know we have questions. I apologize for holding this to the end. I wanted to make sure I got through this in a timely fashion. It didn't go down a rabbit hole, so it looks like I'm right on track. So Jen, if you want to kind of help guide me through getting into some of these questions, let's do it. I'm open for just some discussion.
Okay.
Can I throw a question, Jen? Sorry.
Oh, go ahead, Zach.
I'm just curious about the sub-canopy stuff you've been seeing. I saw that in presentations in Canada, their horticultural symposium in like 2019 is kind of like cutting edge, doing some research there. And I'm curious if you're seeing any data and like, is it worth doing the sub-canopy stuff? And are you getting like grams or are you getting pounds, more when it comes out at the end of the day?
Yeah, so notes on that. I'm actively conducting trials right now with growers in the field, and we've got some at our research facility. So my data is still forthcoming and very preliminary. So most of what I've got is based off of what I'm seeing out from growers talking to me. Impacts range from people telling me I saw nothing to people saying this is a life-changing amount of yield and quality difference, and quality being the biggest driver. So out of everything that I'm seeing, that's really the big thing, is not necessarily even a yield increase, but an increase in the uniformity of the crop and the development of the lower flower buds being much more market ready. So they're getting more per unit crop in terms economically for the same amount of light, because they're able to produce more of that crop as something that can go to the highest quality markets. TBD
Cool.
On everything else, working on that one ourselves.
Yeah,
but I think
cool. Thank you.
That's the big one, quality.
My question is, did other states with legalization, do they have these same lighting requirements? Or is New York relatively novel?
Well, New York is novel in that it started off by basically saying supplemental lighting wasn't something you could do. Right? I mean, they had the 20 light rule, which was effectively precluding the use of lighting in any sort of practical way. So that's that. So we just now are seeing the ability to do that with the proposed rules coming out and the conditional licensing, allowing us to use them in greenhouse space. The biggest difference here compared to other markets is also that it's a greenhouse focus, right? There is no indoor canopy currently.
Mhm.
So that's another key differentiator. We haven't really seen that in other states. Lighting approaches in greenhouse only are very different from indoor. There's a lot more things to consider. It's a different beast. But in terms of qualifying lights that can be purchased, no, that's something that's actually been fairly consistent across a lot of different jurisdictions. Perhaps some of the early markets, Colorado, Washington, California, even Michigan, that wasn't something that was built into those laws initially, but we're seeing that retroactively become part of the regulations. And actually, it's something that's worth noting to you guys as you're thinking about this, is that as these things get built into regulations, what happens is that the utility companies and state programs that incentivize energy efficient technologies become less lucrative because you have regulated that. They no longer have to incentivize you, you have to do it. We rely heavily on the rebate incentive programs to create affordable access to these technologies. So what we're encouraging people to do right now is to really dive into what your plan is for the next 4 or 5 years and to take advantages of these rebates before they start to disappear.
Let's see, Zach asks, can you say more about how the sun produces the same colors evenly? So we're looking at the light spectrum, I'm assuming.
Yeah, sure. So I mean, the deal is the sun is considered to be a black body radiator, right? So it produces, at least in the visible spectrum, there's a small shift, and there's certain wavelengths that drop out, but by and large, you're looking at a very uniform white light. So you have, red and blue and green and all that is very evenly represented. And then there's, something like a 8 to 10% far red component and, like a 1% UV component, depending on where you are. So once you get outside of the visible UV and near far red world, then it's all over the place. But from a visible light spectrum, it's very evenly broadcast.
And this interests me. This is also Zach's question. Lighting needs dependent on genetics. Are there any trends? So as a reminder, there's 3 types of patents: design, utility, and plants. So could you asexually reproduce a plant that needs less light? Are there any plant genetics that where lighting is either you need more, you need less?
Yeah. So cultivar selection is probably one of the most significant factors affecting your performance economically. And one of the key axes of that effect is interaction with light. So as you saw in that yield response graph that I had, you had 3 different cultivars, one yielding considerably more than the other. We do also see the slope of that curve shifting somewhat from cultivar to cultivar. And in addition to yield, there's morphology, right? So we have definitely noticed that there are cultivars out there that just don't like high intensity or broad spectrum light. And if you think about the evolution of cannabis and how it's been bred, that makes a lot of sense, right? We started off with landrace that grew under this sun, and first off, all over the world, right? So high latitude crops are going to get very different light than equatorial crops. So they're going to respond differently. Then we mishmash all this together, and then cannabis becomes illegal. So we start growing cannabis in closets under HPS light. So for decades upon decades, cannabis, which has probably had the most active breeding done by the most decentralized network of people, has been selected for under high pressure sodium lights, which are a narrow portion of the spectrum. They're that green yellow, which is why they work so well, because they penetrate deep into the crop and they heat it while they're doing it. So we've selected for that, but we also selected for a certain intensity as well, because there's only so many HPS lights you can hang from the ceiling before you cook yourself, your room, and your plants, which is somewhere around like 600 to 900 ppfd. Maybe in a really well-controlled space, 1200, but 600 to 900, very common. And that correlates with a cutoff that I see all the time in grows, which is as you start pushing past around 1000 ppfd, 80% of the cultivars in a room are like, yeah, this is great. And then there's like one or two right next to the, yeah, it's great guy that freak out. And you get bizarre morphologies, you get some photo bleaching, sometimes you see actually a negative yield response. So you can have negative interactions with light based off of intensity and on spectrum. Some things, we'll see there's some rules to bleaching. We've got some blogs that you guys can go look into, and I'll talk about this in the next one. But we do see that there's sort of a cutoff of intensity where bleaching really doesn't seem to occur regardless of how much red you pound into the plant. And then as soon as you cross that line, boom, it gets real sensitive to it. Most plants follow that rule. But again, the 80-20 rule kind of kicks in. You have some that I just can't get to bleach. And I have others that even under white spectrum light, as we increase that intensity, they got little white tips. But they're the oddballs. So cannabis is a very phenologically diverse crop, perhaps one of the most heterogeneous genetically of any crop we grow in an agricultural space, certainly from a animal plant population standpoint. So you should expect that just about anything you can think of as something you're interested in, phenotype will interact with that in a bizarre way. So as a final note on this, I know I'm going way out on this, but as a final note, I would say that as starting industry members, probably the best thing you can possibly do for yourself is say, one, how do I want to grow? What are my target light intensities, my light qualities, how, substrates, nutrient programs, everything you can possibly think of. How do you want to operate as a business? Once you've figured that out, then select phenotypes that play nice in that environment. I see a lot of people fight really hard to change their practice in their business to grow a certain cultivar. Cultivars go with the wind, guys. We know how that happens. So better to use your production as the gate and then select your various strains for the market from that subpopulation, because that's how you're going to make the most efficient operation and stay in business economically.
Right. Zach has one more question, but I want to open it up. Anthony, Amy.
Yeah, guys, fire it off. What do you guys got?
Questions? If you're driving or anything and you can't put something into the chat, feel free to unmute yourself. Anybody? No. Okay. So question, UV lights. Does UV, well, we know it has some impact on pathogens. So what are your thoughts on that? Do you guys do anything with UV lights?
Yeah. Okay. So let's break UV apart. This is always a contentious subject in the lighting world. First, recognize that we have 3 different bands of UV light, A, B, and C. UVA does interact with plants, but so does blue light. So there's a pigment in the plant. It's a photoreceptor that called cryptochrome that what's a family of photoreceptors, and they use blue light to make decisions about how the plant should grow and what it should do. And UVA is so close to blue that it interacts with cryptochrome, and so you do see a response. But it's basically what blue light gets at. And blue light diodes are a lot easier to produce, a lot cheaper to produce. They last longer. So UVA is not a very useful tool. On the other side, we have UVC, which is what gives you skin cancer and burns. UVC is where the pathogen control side of the world is, right? It's what barbers use to sanitize their equipment. It's what lighting or water companies use. So its use in cannabis is in any cropping system is exclusively crop protection, and it works really, really well. It can be expensive and challenging to deploy. It requires frequent, like almost daily application. It's really easy to overdo it, just like tanning, right? Oops, 5 minutes too long, now I'm tender. Well, same thing with your plants. You can mess plants up pretty good with UV. but it does go a long way. And given that cannabis often has some of the highest restrictions for what you can apply, even under a federally legal paradigm, right? We extract this stuff, we breathe it into our lungs, we vaporize it. So we just can't use the same materials that other agriculturalists are using for crop protection. And our crop has this nasty habit of growing thick wads of moist material, which makes it prone to challenges. So UV can be a very helpful tool is what I'm getting at. But it also is something that we're all still working on in terms of creating the appropriate tools for using it. I've seen guys use wands and they go and they beam it. One, I wouldn't want to be the guy holding that wand. I hit my leg once or something, and that's an uncomfortable day. You don't know what's reflecting around. So there's a whole bunch of safety issues. But also, that's a lot of labor. Labor is really expensive. So then you need to get into automation. How do you automate so that you cover the crop? Is it is the juice worth the squeeze? Tough to say, but I have seen it used particularly in large scale greenhouses quite effectively where all other control methods failed. It's pretty impressive. The last thing then is UVB. This is the real contentious stuff. Does cannabis respond to UVB and produce more trichomes, more cannabinoids, more terpenes? You know, the straight answer for me is I don't really know. I haven't been convinced one way or the other. We've done some work at Fluence, and we've definitely seen that it produces a stress response. It definitely has impacted yield, either had no impact or it's impacted yield negatively. You can see it in the crops. They don't look as good. Other people have sworn that there's been an impact, and haven't seen a good controlled study along with those anecdotal pieces. So it's like, well, did you just have a really great crop because you cared and you paid attention? We all know that the footstep of a farmer is the best fertilizer.
Confounders.
Yeah, I haven't seen a compelling, well-executed study that had a good baseline control, and I would love to see it. But from our research, we haven't seen an impact, but we've had a lot of people who have criticisms out of the methodology, which seems to be what happens anytime someone pokes at this. So the straight and narrow is, I don't know that it does or not. Most UV fixtures produce a very small quantity of UV, so you get a little bit. My gut tells me that there are so many other limiting factors to production that have massive impacts on the economics that I would be focused on those. Getting your cultural practices tuned in, getting your cultivar selection right, optimizing your light delivery in your training, and fixing post-harvest so that you're not blowing all the terpenes away, right? That's how many times do I see people spend millions of dollars on a facility, and then I walk into a dry room and it's like, wow, that smells great. There go all your terps. So that's not good.
Yeah.
They should spend some more money on that dry room instead of thinking about UV.
Yeah. I want to just say I put my email into the chat. This is being recorded, so if you would like the link to our YouTube channel, where we will have this presentation as well as all of our other presentations for Cannabis Industry Meetup, you can email me, and I'll also, if you are interested in the PowerPoint presentation that Jason has put together, feel free to email me. So any other questions for Jason? This has been a lot of information, I know, but it's been super helpful. Any other questions?
Oh, this is so great. Thank you, Jason. I got to hop off, but I'm excited to rewatching, keeping the study on the lighting going. So thank you so much for
Yeah.
Sounds great. Thanks, Zach. Take care.
All right.
Well, it looks like everyone is good, or at least they're holding their own on silence. So
yeah,
I guess we could call it a wrap. Thanks for taking the time to listen to me, y'all.
All right. Thanks so much. All right. Have a great night, everybody.
Bye, Jen. Bye, everybody.
Bye.